This is the part of class where we're just counting down the seconds. Welcome back, everyone. Hello. Looks like we can get started. Welcome back, folks. Whether you're in person or if you decide to visit today in the classroom, welcome to the classroom. So today's class, we're just continuing on where we left off in section 6.1. We have two more big graphs that we want to plot just to get more comfortable with those plotting techniques. Then we'll also look into this quick application just to kind of take a mental break, but also think about some of the applications to what we're doing with some of this plotting. After we finish off section 6.1, we'll go off into 6.2. This is a bigger section, so I have the feeling we'll possibly finish it late on Monday's class or possibly somewhere early on a week away, Wednesday's class. Make sure to take our time with these because, well, there's 6 plots altogether. They look sometimes pretty similar, like the sine and cosine, but another way it's really kind of wildly different in the strategies we go to plot them. But any questions at all, folks, to start us out today before we jump back in? Okay, let's get started. So we left off on this problem here, part B. I copied this down just so we can have another visual on some of the ideas on what we're doing. We're graphing not just sine and cosine, and this will be the same in section 6.2, but these types of transformations of sine and cosine, which is lovingly referred to as the sinusoidal function. It's kind of a weird word. I'm still getting used to it after all these years. Really, this is just connecting with the pre-calculus 1 material or college algebra material on transformations of graphs. We've seen already that, for example, if you put a negative sign in front of a function, if the function looks like this, the sine curve, it's going to reflect across the x-axis and look like this. That's why on our very first plot for -3 sine pi x minus pi, sine starts off going down, not up, all due to the negative sign. And this information here is just capturing a lot of those other properties that we've learned in pre-calculus 1 about transformations of functions. So we'll try out 2 more problems. Pretty much these instructions are repeated verbatim. Another thing I want to point out, just so that it's not weird when you take a look at it, I felt like the actual problems in the textbook were great, but I didn't like the instructions because I felt like being a little bit more specific on the instructions really highlights what we're trying to go for on a completed plot. So I wanted to be more specific, and because of that, on assignment 6.1 and assignment 6.2, these go a little bit differently. If you click on this, it's a PDF. Similar kind of problems in the book, but I just again want to be really specific on the instructions. So these are homebrew problems now with the same kind of instructions that you're going to see in the lecture notes. That way you'll know pretty much what you're doing is the same thing we're doing in class as well. It'll be pretty specific here and same instructions as you see right over here. So let's get started. The instructions are kind of designed to help us really just begin the whole process. We want to find the amplitude to begin with, and that's needed because that's going to tell us how the scale works on the y-axis, the vertical direction. The amplitude is determined by this factor here. It'll be the absolute value of that factor, so whether it's positive or negative, we'll report a positive number. That makes this problem kind of weird, right? You can always interpret that there's a 1 times cosine, so this means the amplitude on this problem is 1. And just a reminder, we'll write out amplitude, short for AMP, short for amplitude. Next thing we want to deal with is the period. And to get the period, we really do 2 things. We use the fact that the period of sine and cosine taken together is originally 2 pi. But then this factor right here, multiplying x, changes the period. It's either going to cause an expansion on the x direction or a compression on the x direction. And here is how it goes together. The period will be 2 pi, the original period of cosine, divided by whatever that factor is. And that factor is pi over 6 in our problem. So we'll begin by writing out period equals p for period. Take 2 pi, that's the given part. Then divide immediately by pi over 6. A little bit of arithmetic, we'll have 2 pi times 6 over pi. Kind of the pi over 6 is sort of helpful in this problem. Pi cancels and you get 12. So nothing too wacky. That's kind of a convenient number to work with for us. Next thing we determine is phase shift. That'll be on our way for the next part of plotting. Any questions at the moment getting these two elements? Okay, so we're pretty much just walking through the pieces of the function, determining how it's going to affect the plot. So we have a pretty effective way to just plot this all in one go. Phase shift, I'll abbreviate like before as PS or P dot S dot. It's going to be determined by this number here. And this is tricky because whatever the phase shift is, it comes down here. We'll mention this a lot in the notes just to be careful with it. And we always flip the sign. Then the next thing that's tricky is we also divide by the B factor right here. So B is still affecting what's happening on this phase shift. And we get all together phase shift equals, in our problem, that plus becomes a negative. We'll take the pi over 3 we see there. Just to try and determine what to highlight here. Let's keep the color coding similar. Divide by pi over 6 once again. And that's our phase shift. Let me just fix the penmanship there. That was meant to be a 3, if you're wondering. So this will be kind of nice because once again, pi is just going to cancel out. This will be negative pi over 3 multiplied by 6 over pi, which means phase shift on this problem is negative 2. Essentially, what it means is we're taking the cosine curve, moving it left from its starting position by 2 units. Period also means it's being stretched out. The period is not 2 pi, which is approximately 6.28. It's almost double that. But the amplitudes stay the same. We're not stretching it at all in the vertical direction. It's exactly how it originally was. And that arrow is kind of a distraction. Let me see if I can kind of target it better. The positive right here becomes a negative, so always flip the sign. Honestly, it's the easiest thing to miss on this. And if you did miss that one part in an exam setting, there's partial credit on these kind of problems. So these are the first steps in order. Get amplitude, period, phase shift. Pretty much that is what this is asking. It's also asking for a midline equation. And midline equation is going to be the horizontal line y equals d. It comes from this part right here. We have no such part, but you could put in plus 0, which implies the midline is the equation y equals 0. So repeat on that one. Next problem will have something different than a 0 in that position. So after all this information, we can put this together and start plotting. But sometimes it's good to organize even more on this. Here's what I would personally do to organize this further. We want to know where the plot starts, so I'll often write this down on the notes. The start of this plot is going to be exactly whatever we said the phase shift was. So that's going to be a negative 2. Essentially, I just copied this information in. We also want to know when we stop plotting because we're only plotting this that says over one period. So one length of 12 is what we're plotting. If you plot more, no harm done, but it's good to know when you could just stop for full credit. The end is going to be whatever the phase shift was, plus whatever the period is. I don't know why I said was. The phase shift is still negative 2. So it's going to be negative 2 plus the period of 12. So the plot ends at 10. So this is all x-axis information. Y-axis information was the amplitude 1. And the final bit of information we need is, well, how far do we go to get all the interesting points? Because our curve must include the exact x-intercepts, exact values on the x-axis, indicating x-intercepts, as well as where the maximums occur and the minimums occur. All that information is found by doing this one computation, finding the increment. The increment means we'll put a tick mark at -2, but how far do we need to go to get to, say, the x-intercept? That's what we're incrementing by. And the increment is this magical number, 1/4 of the period, 1/4 times p, which will be 1/4 times 12. So an increment of 3 tells us, go a distance 3, and you get to all of the important information, filling out this last sentence right here. So a lot of preparation just to get started. But once you get the hang of doing this, we'll do quite a lot of these in 6.1, 6.2. It becomes just kind of a process, an automatic thing that we'll do. Essentially almost second nature. With all this done, let's start by writing in the horizontal axis. I'll put in this information first and then the y-axis. We're starting at -2. Increment means add 3 to get to all the new tick marks. So add 3 to this value right here. Sorry, my mouse cord is giving me trouble. Add 3 to this right here. We end up at +1. Add 3 more, 4. Add 3 more, 7. Add 3 more, 10. I notice that's where we had to end on, right at 10. So there's going to be 5 tick marks for essentially every single function we plot. So it's kind of nice in a way. Now, there's the x-axis. It came from all of this information right here. You have to throw in the y-axis. There's 0, but we usually don't put it in as a tick mark because it's this, a gigantic tick mark in a certain sense. So here's our y-axis. And this is where the amplitude information comes into play. This sets the scale of the graph. +1 will be here. -1 will be down here. Well, we're about ready to start plotting. Any questions first before we jot it down? Yeah, go ahead.
Why does the increment have to be 1/4 of the period?
That's a great question. It turns out to get to these parts, the x-intercepts, maximums and minimums, it's always exactly 1/4 of a period for any function, sine and cosine, even a transformation of it. It came from basically this graph right here. The graph of just cosine alone is 2 pi. But when we take 1/4 of pi, we got pi over 2. And so I think the better way to answer your question is because cosine and sine have either a max or intercept at the start, then 1/4 into the period, then next is going to be a maximum 2/4 into the period, halfway, then either an x-intercept or a maximum 3/4 into the period, and then again, either a maximum or an intercept. For the sine graph, it went a little differently. It started at an intercept, a quarter into the cycle, pi over 2, we're at a max, intercept, minimum, and then another intercept. So really it's just inheriting those basic shapes of sine and cosine. They hit all those interesting spots, 1/4 of their period. So that means even if we transform it a whole bunch like this one, it's still 1/4 of the period. This one hit all those interesting things if we move the distance of pi over 2 over. And this one will do the same if we move a distance of 3 over from the starting position at -2. You might notice there's a blue circle turning around my red dot. It's not always a good sign. That sometimes means my computer is doing something weird. Okay, it ended. So hopefully all is good there. But does that answer the question about the 1/4 period?
Yes, I think so.
Awesome. Again, it's kind of a mistake.
On that. So on the 1/4, if the wave stretches out, would it, how, would it still remain, how would that work?
It would still be 1/4 of the period, even if it got stretched out.
Okay,
That's kind of what's happening on this one. This pi/6 factor is going to stretch out the curve because the original period was just the 2 pi right here. And double pi is at roughly 6.28. But the pi/6, once we divided it in, it stretched it out to a distance of 12. But even though it's a distance of 12, we still take the exact formula right here, 1/4 of the period, to start from an intercept, we'll go to a maximum, then another intercept, a minimum, and then another intercept. Again, that's usually kind of the mysterious part about this. And in the document right here, summary applied techniques, kind of just like we mentioned, a cookbook for doing all these. That's what this stuff is talking about. Also calculate 1/4 of the period, because that's where you're going to get all your interesting elements in the plot. And when we go to cosecant and secant, you still calculate to 1/4 of the period here and 1/4 of the period here. It's tangent and cotangent where it changes. Turns out tangent and cotangent graphs are different enough. We get to the interesting things, a vertical asymptote, then an intercept, then another vertical asymptote, halfway through the period. These will be the last two functions that we'll discuss. But does that help answer those questions so far?
yeah, it does, thank you.
Yeah, absolutely. Well, let's give this a try. So we have all the information set to put the axes down, the vertical axis and the horizontal axis. There's still one fundamental thing that's critical about all this. You need to know the general shape of cosine itself. So it doesn't hurt to just sketch this out. Y equals cosine x. Sure, we plotted it before, but we need this mental image. So I'll put it orange just to say this is about what it would look like. Cosine starts at its maximum value. It dips down to intercept, hits a minimum value, increases to another intercept, and ends on a maximum value, ending at 2 pi. This one changed a little bit. It got shifted to the left. It got stretched way out, vertically no change, but it's still the same basic shape. Always check what's in front though. If there's a negative, it's going to flip around on us. That was our part A. We'll see it again on the next part. So here is what goes on next. When we go to plot ours, because it's a cosine function, at the starting position, it's at its maximum value, right up here. And we didn't put any tick marks except the ones that were relevant. 1/4 into the cycle, that's here on the graph to the left, we hit an intercept. And same right over here, we'll hit an intercept as well. And you might be wondering, how do we know that this is correct? Well, there's a good check. This is x equals 1, and you can put x equals 1 right there. If you did, this would be f of 1, which is cosine pi/6 times 1 plus pi/3 can turn into 2 pi over 6 to get a common denominator. This would then be cosine 3 pi/6. But that means it's cosine pi/2. And we know cosine pi/2 is 0. Sine pi/2 would have been 1. That's exactly what we're seeing here. Plug in 1, we get 0 on our function. It's not at pi/2 just because it's been transformed. It's been stretched, relocated, and all sorts of, well, just those two things primarily. So cosine goes down here. Move one increment over, 1/4 of the period, which was 3, what we called the increment. We're at the minimum value, so we go to -1 here. Move 1/4 of the period, add 3, 4 plus 3 is 7. We're back on an intercept. That's what happened right here. It's just the same curve stretched out. And then move 1/4 of the period out to 10, and we are back to the maximum. Just like we'd be back to the maximum there if the curve didn't get stretched out or had a phase shift. So we're almost there, folks. This is where the artistic side of us has to shine just a little bit. We have 5 points matching the 5 tick marks we put down. And you don't have to be an artist when you draw this. There are some ways you could lose points though. You would lose points if you did this. Not because I kind of didn't even go through that point. My hand got a little shaky there. I kind of missed this point too. That's not the problem. If you sort of miss your point, I wouldn't worried about that too much. This doesn't give us credit because cosine is not a sharp curve. It's a smooth curve. It's got to look like that. Imagine it's the profile of some crazy wild ride. Someone designed this ride at a theme park. They would probably be banned for life on designing roller coasters. So just make sure it's kind of rounded out. On the top, it dips down rapidly. Then it slows down when it's losing altitude. Then out here, when it goes through 7, it's increasing rapidly. And then it slows down as it's gaining altitude out here. Again, it doesn't have to be perfect. Just do your best freehand sketch. It could look kind of awful. It might miss a point, but if it has the same general idea, that it's a smooth curve, then you'd get full credit. But we did it, folks. This is a complicated curve. F of x is cosine pi over 6x plus pi over 3. And those are the steps to getting the plot down. Any questions at the moment surviving this one? Okay, what we should do immediately is try out another one. Practice is what makes these really come together. And the good news is that in section 6.2, we'll go into the cosecant and secant functions. But when you plot cosecant and secant, really you're reviewing this stuff. This turns into a guideline for secant and cosecant, so it's kind of cool in a way. But first we should do something that is just a little bit different from all the others. This is the part that's a little bit different. It's a transformation of sign, and it has lots going on. The negative here is going to reflect it across the x-axis. 2 is going to stretch it out vertically. Pi here is going to affect the period. It's going to compress this one. And the negative pi over 6 is going to relocate it as well. So a whole lot of things we have to run through. Let's run through the just key pertinent parts. Instructions are designed to just get us to where we need to go. It's not trying to give us information in scrambled order. You need the amplitude first for the y-axis. So AMP for amplitude is absolute value of this number right here. So negative 2 goes in, comes out as positive 2, and that's one of the 4 parts we need right here. Next is period. Period gives us a lot of information, tells us how long we're going to sketch through. And when we calculate 1/4 times the period, it tells us where to get to all of these important values that needs to be on the graph. So to start off, period on this one involves that number right there. First, it's 2 pi. Let me put that in black just to communicate for sine and cosine, even cosecant and secant. You start off with period 2 pi in the numerator, then you divide by whatever this number happens to be. Kind of a nicer division this time. It's just 2 pi divided by pi, so the period is exactly 2 on this one. Last is phase shift, yellow, just because I run out of colors pretty fast on this. So P dot S dot for phase shift is going to be equal to, we take whatever this number is. We have to be very mindful that we take the opposite sign. And so that means we put in positive pi here. It's not the full story though. This pi actually affects things. It affects the phase shift as well as the period. So that pi that we spotted divides into 2 spots. And you'll know this is a pattern. The more you practice it, the more it's going to become more muscle memory. If you divide by pi in the period, you'll divide by pi in the phase shift. Looking at the last problem just for guidance, we divide by pi over 6 in the period here, pi over 6 in the phase shift here. Now the very first problem, we divided by, well, we didn't have anything to divide by here. So that was a combination breaker. So let's focus on the ones that actually had a scalar in front of X. So that's a common feature on these. And it tells us finally, phase shift on this one is 1. It's not the full story because we also have the midline equation. So I'll write out here, midline. This is essentially the only new part in this problem. The +5 is going to take our ordinary sine wave and just move it up, dragged by 5 units vertically in that direction. So that means the midline is y equals 5. So this is the first summary information. Information you put here on the right is optional, but I feel like it's a good thing to put down. It organizes our thoughts, makes the notes more readable, and it helps us get the full sketch down. Any questions at the moment so far? Okay, all of our other problems had midlines, but we never did anything with it. For example, on the last one, the midline was the equation y equals 0. The reason we didn't do anything special with that is the equation y equals 0 looks like this. It's just the x-axis. It's kind of hard to plot it. So this is my best way to communicate. This is where y equals 0 is. It's the line that the cosine curve or the sine curve is oscillating about infinitely many times. This time, it's oscillating about the curve y equals 5. So we'll have to be really mindful of that when we go to plot things out. Before we jump into the plot, let's talk about where it's going to start, where it's going to end, and how much we increase by or increment by on the tick marks on the x-axis. So the formula for the start is the same, phase shift, which was 1 on this problem. We're going to end this at the phase shift plus the period, just because the period tells us how long of a length we plot across. Kind of wanted that one in green as well. So this is going to be equal to 1 plus 2. So it ends at 3. And you might think, well, that's kind of a no-brainer. If you start at 1, you're plotting over a length 2, definitely you're ending at 3. But just writing it down just gets it into our head. So anything we do down here, we'll know if we go beyond 3, something's amiss on the plot, or maybe I'm in the second cycle and we didn't have to go that far. Last magic ingredient, the one with the most questions, is the increment. It's 1/4 of the period, which means it'll be 1/4 or 1/4 times 2, reducing to 1/2 altogether. Our information is slightly incompatible, and we'll see in the next section where this goes a little bit more tougher. There's nothing wrong with 1 and 3, but if you want a least common denominator, you could write this as 2/2, and this one as 6/2. It's just one way to do it. As long as you're giving me exact values, I don't mind what your approach might be. Other people might keep it this way, 1 and 3, and just call this a 0.5 and work with decimal values. I think that's probably the most convenient on this one. It's exact, so it qualifies. Let's work with decimal values on this plot, just so as a way to say that's totally fine if you prefer, and you're using the exact value. So if this was a third, it'd be less convenient for me to use, or a 7, some weird number like that. Next piece of information we want before we just launch into the plot is we want to organize our thoughts. We're plotting y equals sine. It's a transformation of this basic curve. Sine increases, hits an intercept, then starts to, let me say that again. Sine increases, maximizes 1/4 of the period, then decreases, hits an intercept, minimizes at -1, and then increases to its intercept. It's not exactly what we're plotting, right? If there's a negative, we flip that whole picture across this x-axis. So the mental picture we really want to have is negative sine x, whether it's in your mental chalkboard, just a picture up in there. For me, I'm not great at visualizing a whole bunch of information in my head, so I would just sketch it out on the margin as just a quick reference, unless I just felt really confident. maybe I've done dozens of them. At that point, I'd feel confident enough to not sketch this. But negative sine x would have this curve. Just a really fast sketch like this can be really valuable for us. Now we bring it all together. Because the midline equation is 5 and everything got dragged upwards, what I would want to emphasize is mostly quadrant 1 this time. So this is where the curve is going to live. Let's start by putting down the midline equation first, settling the y-axis. So we'll go up a distance of 5. And this dashed line, if we put an equation to it, it's just y equals 5, the equation of any horizontal line. At height 5, you just throw in the 5. Now, amplitude gets involved in an interesting way, right? The amplitude tells you how high you go up from whatever the midline is. And this time, it's not the x-axis. So if the amplitude is 2, we go up to 7. We just add 2. That's going to be the maximum of the plot. And we go down to 3. So that's the new thing. If you think about it, we didn't do anything too different on the last problem. It was just that y equals 0 is something we're just prepared to go up a distance 1, down a distance -1. It just didn't feel unusual. Or in the prior problem, this was y equals 0 here, and sure, amplitude is 3 meant we went up 3, then down 3. It just definitely feels different, though, when you're using y equals 5 and not the x-axis, but same exact idea. The amplitude was 7, we would have gone up 12, and gone up to 12, and down to -2. Well, y-axis, the vertical one is done. Any questions so far? Okay, at this point, we can see this information. This is just telling us where everything is on the horizontal axis. Working in decimal form, I would first put a tick mark here, but not label it so it's not a distraction. That's going to be 0.5. Add 0.5 to that, we get to 1. I'll put the tick or the label on that tick mark. That's where the start is. And this just tells us wherever we are, add that same increment value, 0.5. So here it's 1.5. Here it's 2. 2.5. 3. We end right at 3, so we have the 5 tick marks that we need to plot this curve. We're just about done. We just need a curve that looks like this. So sine, whether there's a positive or negative on it, is always going to start on the midline. It just happens we're also starting at 1. So this is the first point we plot on the sine wave. Essentially, what we plotted is that location, but it just got moved around in our transformation. We move over to the next tick mark. This is where we're going to hit the minimum. So that's going to be at height 3, where that blue label is. Move over to this. This is where we're going to intersect the midline. So we're going to be over here now. Move over an increment, 0.5. We're at the maximum value. So at height 7 on this one. Finally at 3, we're back to the midline equation. And so it ends here. Notice this problem had different wording. It said midline equation intercepts, and that's because there is no x-intercepts on this curve. If we go to plot this one out, it would look like this. So that's finally -2 sine pi x minus pi plus 5. Takes a mouthful to say, but it takes even more work to plot. But these are the organization that we're going to do pretty much on every single thing we plot, even in section 6.2. We'll start with the core information, organize where we start and end in the increment, think about what the curve should look like, and then go at it in this way. Any last questions at all, folks, on the conclusions here? Okay, probably what questions a lot of folks would have is, why take all this trouble to plot these kinds of functions? Well, it's one way to think about it is, it's very useful in applications to take points like these and see how to do a curve to fit to it. Another way to think about why we're plotting it is just to gain a better understanding of what sine and cosine are really doing. And another way to answer how the plot helps us is in chapter 7, we're going to be solving trigonometric equations. And here's one. Here's a trig equation that goes -2, I'm just copying this whole function, -2 sine pi x minus pi plus 5. Now it's an equation with equality. And let me put something bogus here. Equals 2. So if you see this equation, but you know how to construct the plot of the curve on the left, you know immediately this has no solution. The way we can reason through that immediately is 2, if we plot on the curve, looks like this. There are no points of intersections whatsoever. If we had 3 here instead, then this would have looked like this. That's hard to move. There is one intersection. In fact, there's infinitely many because the curve continues on and on. But 1.5 would be a solution, and we'd have a way to specify the infinitely many solutions. So knowing something about the geometry of the curve itself, which we're studying through actually literally sketching it out, tells us a lot about other objectives down the line. We can look at a glance, considering the graph of the curve and an equation, whether there are solutions whatsoever. No reason to even work harder on this one if there is nothing where it's being led to. But this is the end of section 6.1. I want to show one more scientific kind of application using scientific data. But any last questions at all before we close out the notes here? Okay, and maybe just so the notes don't look mysterious, let me take that line off. Okay, one more save. And as promised, we'll take a bit of a mental break because that section is pretty intense. We'll review plotting sine and cosine again in section 6.2. But for the moment, let's look into sinusoidal curve fitting to scientific data. This is a GeoGebra algebra application. I'm not sure if I'm saying that right. And this one was made by Tom, okay, I'm not going to pronounce that right either, Oshweed. So thanks goes out to Tom on designing this one. I forget that there could be ads. Sorry about that. I try not to show you random ads in class. But here's some random scientific data. Let me see if I can move this around. I can't quite get it off the page. Let me just sort of disappeared a little bit. Here's some random scientific data. It's these black points that are being plotted here. And this could represent all sorts of things. This is pretty noisy looking data. But our objective for data like this is to try to fit a curve to it. If we suspect that these data came from a process that's periodic, something like seasons, waves, or maybe something more complicated, maybe a biological process that repeats every 36 hours, just a random statement, or maybe something in electronics, something that happens in milliseconds. Maybe we're reading a voltage off a transistor, we're outputting data. You might have data that looks like this. If you know it's periodic data, you want to fit a sinusoidal function. Here it is right here. Notice it's in a slightly different format. The way our author goes is bx minus c. This has b times x minus c. Honestly, that's probably the better format. I'm going with this just to match up the book so the reading is not mysterious. But this kind of answers why the phase shift does involve b. It's a part of this. If you factor out b, you would be dividing it in this location. So we're just looking at one of the same kind of functions, slightly different format, but same algebra. Our objective is to get this curve as close to all the points as possible. So we wonder, well, the first problem with the curve is that it's way too low. We have A, B, C, and D to work with. And I kind of spilled the beans because I messed with D already. If you manipulate D, this is just telling us what the height of the curve is. That's the midline equation, just like on the very last problem. So moving D around, we can have maybe a slightly better fit to this data. Okay, it looks like some pretty messy data. This is going to be a challenging set of data to fit towards. I'm going to cheat a little bit, see if we can get a better example. I think this one might be a little bit funner. The data looks a little bit more predictable in a certain way. Not that the last problem was bad, but I didn't want to start off with like the hardest one I've seen personally for our first one of the day. So here's our data. The curve does go through one point, but that's not exactly what we want. We want the curve to go through as many points as possible. I say that in a weird way, not necessarily go through as many points as possible, be as close to as many points as possible. So the height of this one looks like it's about right, but the curve seems too compressed. We have to stretch it out. And the stretch factor is B right here. So let's take a guess. Should we make B bigger or smaller? Any guesses on what we should do on that? Guessing's hard, so while we're thinking about it, let's put down a formula. Period is 2 pi divided by B. And Chen says larger. Let's check that out. So we put a bigger number inside here. In other words, move the slider to the right to make it bigger. The bigger the denominator, the smaller the whole thing is. Let's see what that looks like. So the bigger the number, the smaller the period. Looks like it's compressing it down, almost like an accordion. So what we want to do is make the period bigger. The way you make something bigger when B is in a denominator is you make the denominator smaller, it turns out. That's a lot of backwards and forwards thinking, lots of reversals of expectations. It's kind of a confusing process. But here we go, we're stretching this out. Same exact formula that we used to plot our curves. And the more we stretch this out, the more nice it might look. You know, maybe about there doesn't look too bad. It's hard to get it just right though. So if I ended it right there, we might decide maybe it's not in the right location. We would try to now affect it through a phase shift. The phase shift is going to be affected by this part right here, the C coefficient. So if we take the C coefficient as a slider, just literally going to drag it to the left and to the right. So that's kind of nice. So where are we going? Well, maybe about here. The more I drag it, the more I might want to mess with B a little bit to make it either more compressed or less compressed. But we're not trying to get it perfect, just good enough. One other thing you might decide is maybe the vertical scale could use a little bit more stretching. The way that's associated is through the amplitude. The amplitude is the absolute value of whatever you put inside here. So that means it's moving around the A coefficient. If I make this smaller, it compresses vertically. We can kind of just see it on the graph. That's kind of fun in a way. Make it bigger, and it's stretching out, and maybe about like here, starting to look like not too bad of a model. So it looks like it's going through a lot of these points. Some of them maybe not so well, say like out here, maybe down here, but it's a pretty decent model. It could be something that you might use to make forecasting with, or I don't know what the word is for reverse forecasting back in time. So this is just another way to see what sinusoidal functions are all good for. Thanks again for Tom on coding all this up for us. And if you're a fan of statistics, if you've taken statistics already, or if you know you're going to take a lot, say like regression analysis or time series, this is a time series type of analysis. Click here, and this is the best fitting curve. Notice not quite what we might have thought, but the more I look at the green curve, the more it looks, yeah, this would be a pretty good one. There's an actual mathematical way to optimize and get that specific equation right there. So checking our coefficients, they have 1.08. Our scale coefficient affecting period was 0.128. We're not too far off. On the height, we're pretty close on that one. And this was affecting phase shift. Ours, oh, that's 26.9. Oh, hang on. The value got distributed in to the group right here. So we'd have to factor out to at 1.487 to see the numbers better. Probably math we don't necessarily need to do on this one. But this is a fun one to experiment with just to see how all these elements taken at once are really just coming together for curve fitting. Again, that's good to see at a glance what these curves look like, but it's also comforting to know there is a definite formula for all this kind of stuff. So that was our fast mental break before we launch into another complicated section. The next section looks like we have 5 minutes, so I won't take too much of your time. We'll start this fresh when we come back on the class on Monday. But I just want to take a couple minutes to show you kind of how this goes together. If you want to plot beyond sine and cosine, say you're dealing with cosecant, your first thought would be, how do they relate? Y equals cosecant x is 1 over sine x. That means there's some nice, interesting relationships here. You'll know from pre-calculus 1 that this is a function which will result in vertical asymptotes precisely when sine x goes to 0. So the best way to plot cosecant turns out to be, you want to plot sine first. We'll redo the plot when we come back next class, but here's the big punchline to this. The plot of ordinary sine goes like this. We have 1/4 of the period at pi over 2. We start at here, we go to a height of 1, dip down to a depth of -1. Pi over 2 is a maximum. Pi, we're back to the intercept. 3 pi over 2 is a minimum. 2 pi, we're back to an intercept. And this is the sine wave. But if cosecant is 1 over sine x, here's what you get to do next. Vertical asymptote occurs exactly where sine is 0. So this is a vertical asymptote. It occurs here, right at pi, so that's another vertical asymptote. Sine goes to 0, 2 pi. 1 over 0 is undefined, and graphically, geometrically, it looks like this. Vertical asymptote. Next cool thing is sine pi over 2 is 1. That means cosecant pi over 2 is 1 divided by 1. It's still just 1. So it matches right at this point. Then it gets repelled away and approaches the asymptote on both sides. Same idea down over here. It intersects right on the sine wave, and then cosecant goes down in this kind of way. So we'll review how that goes, take another look at it when we're refreshed and coming back on Monday. But the cool thing about this is if you're plotting cosecant and secant, you just use sine and cosine as your guideline, and it informs you what the plot looks like all at once. So we'll still practice plotting sine and cosine in a certain sense. Our end goal is to do transformations, but if we can transform sine into the right spot, we can transform cosecant as well. So it'll be very similar problems, just a little bit extra. This is the new part, vertical asymptotes, meaning no amplitude on these. But any last questions at all, folks, before we call tonight? Okay, well, have a great weekend, everyone. For things coming due, section 5.3 is due today. And thanks for the student. I realized I forgot to push the due date away on this one. It's supposed to be 1 week from when we finished it, and we finished this one officially, that one tiny part, on the start of Monday's class. So the 5.4 section is due on the 29th. If you felt like you were rushed because I forgot to put in the right due date, and you want to make any changes, but you already turned it in, you can make those changes and turn in a revision. That would be just fine. But have a great weekend, folks. We'll be back to 6.2 on Monday. And here's this back for you. I was able to get the original.
Yeah, I was looking at it earlier today, I think it was, and yeah, it was just me forgetting to write down the light science stuff.
Yeah. I've done that several times in class already. It happens.
I actually do for reason. Want to make sure I have